Hello, my name is Andrew.
My name is Janan.
I'm Sapir.
And this is our RFID pet feeder. Now the inspiration for this project was I have 2 dogs at home and I'm gone for about 10 to 12 hours a day. And I get really worried that they don't have clean water or that they can't eat on the regular eating schedule. With last semester, before I transferred, I was about 5 minutes away from campus, so I could easily go home, make sure they're all good, and go back to campus. But now I'm relying on friends and family to do it, and it's becoming very stressful. So this project provided a perfect opportunity to make a real solution. And also for this project, we had to make a product that could also be used for the disabled. And Janal's going to tell us a little bit about that.
Okay, so imagine you're in a nursing home and you're in a wheelchair. You can just come up to our device and you can scan your RFID chip that's going to be on your wrist, and our device is going to dispense whatever food or liquid you need. And so you're not going to need anyone else's assistance, and your caretakers or caregivers can just restore or refill the food storage or water storage or whatever material that needs to be restocked. Another example, for the visually impaired, we can add a speaker to our device, and then it can tell the user whenever the food needs to be refilled or whenever their pets are fed or need to be fed. So yeah, it can be adapted in various ways. Now Andrew's gonna go ahead and tell us about the food distribution.
All right, to the left here, we have our food distribution system. And first we have our food storage container with a propeller mechanism. And underneath we have our dog bowl that is essentially a drawer. And this is controlled by a custom-made 4-bar mechanism. And both mechanisms are powered by 12-volt brushed motors. And to activate the whole system, the dog will have an RFID chip attached to their collar. And they will go up to the machine, and the RFID module will scan the RFID chip. Now this will send its serial number, or I think of it like a social security number, to our microcontroller. And it essentially acts as a condition in our state machine that will then control the amount of food being distributed and the time interval in which it can be distributed. And Janal's going to talk to us a little bit about the water system.
Okay, so this is our water distribution system. So basically what it does is flushes out the water every 8 hours and refills the bowl. So this is our water storage, which is about 2 gallons. And then we have a water flow sensor right here, as you can see. And then this sensor communicates to our microcontroller, and then we use that data as condition to know like how long our solenoid needs to be open to fill up the water bowl with the desired amount of water. And we actually have 2 solenoids right over here, and they work together in pairs. So basically, when this solenoid opens, it fills the water bowl, and when this one opens at the same time to dispense flush out the water from the water bowl. And basically this system would be ideally connected to the plumbing of our house, so we don't have to manually get rid of the water, and it's all automatic. And now Sapir is going to talk about the electrical stuff.
So I'll talk about our whole electronic interface here. The microcomputer in this case that we use is the Jetson Nano. And we chose this over the RPi Pico because of the fact that we were so keen on using RFID in our project. But these RFID tags and module work on CircuitPython libraries, and the Pico is strictly MicroPython, which is the Thani IDE. And it also has a very small amount of RAM. It only has like 256 kilobytes of RAM, whereas the Nano has 4 gigabytes of RAM. So this allows us to download the libraries and packages necessary. But this also does mean that since it's not a microcontroller, we have to download an operating system on this. So we downloaded Linux, Ubuntu on here, and had to download Python and pip3 like manually. So that was a huge hassle, but it's done and it works. So now let's talk about the spaghetti wires that we have here. The Nano is powering the power rails and ground rails here on the breadboard, and the power rails and the ground are all common for all 3.3 logic devices. So that includes the RFID module, the relays, the flow sensor, as well as the in pins of the motor controller. So these are all getting power from this the power rails on the breadboard that come from the Nano. And so the RFID module and the OLED screen that we have here both communicate via I2C, and the Nano has pins 2 and 3 available for I2C, but this actually works as a bus, so we can connect multiple devices up to pins 2 and 3, the SDA and SCL pins in the Nano. So that's what this breadboard here is, basically connecting all the pins from the OLED and RFID reader to pins 2 and 3. The relays and motor driver are used to actuate our 12-volt devices, which are our motors and solenoids. So the relays are basically used as a switch, configured in the normally open configuration, because when we apply 12 volts to the solenoids, they open. So we want the circuit to basically always be broken until we apply that voltage across the solenoids. So yeah, that's a brief overview of our electronic system. Now we can run the code and show you a demo. So let's turn this on. Testpeter.py, run it. All right, so as you can see, the states all show 0 right now, which means the dog's not allowed to eat. So if I scan this tag right now, the OLED screen shows that the dog has already eaten and nothing happens. But now the dog has been actuated to eat. So if I scan this, it rotates the motor and it's gonna wait 3 seconds, and then it's gonna dispense the food and bring it back. We brought it back for now just for demonstration purposes, but in reality, it'd stay out for a while and let the dog eat and then come back. And then you can also slightly hear the clicking sounds, but that's the sounds of the solenoids actuating. So we have them set to about 25-second intervals for demo purposes, but they're opening and closing off of a time base. Yeah. And that's it.
Yep, and then also, so we want to talk a little bit about what we learned in this project. And I think Janelle's going to start us off with that.
Sure. So our project is basically a combination of 2 classes for mechatronics and for mechanical design. So basically, we designed this whole thing and our crank slider, and then after that we integrated all the electrical components, so it was like a huge challenge for us, and we learned a lot. I personally learned a lot on how to like integrate both sides of the systems. Other than that, in our labs, we've only learned on small pieces, and then over here we worked on different subsystems, which was really challenging to put together and like make sense of all the wiring using breadboards and just organize everything so it makes sense. It also helped me learn how like circuit diagrams can help me really visualize all the wiring before actually putting it all together. So yeah, it helped me learn a lot, and then Andrew can go ahead and talk about his experience.
Yeah, so going on what Janan said, in lab, we essentially learned how to do each little component of what we implemented, but at a very small scale, and it wasn't integrated. So learning how to take a bunch of little things and put them all into one big system ended up being way more complicated than I originally thought. And the other big thing for me at least was we were used to using the Raspberry Pi Pico in lab, and we ended up having to pivot to the Nano, and then that made us pivot to new coding language and to a new operating system. And it just, once you figure out one challenge and you solve that problem, ultimately more challenges come up, and it's just about knocking them down one by one. And so really learning how to be organized and to work through all that was a big challenge, and really learning you can't really know everything going into a project, and you got to learn as you go. Thankfully, we have Sep, who was working on a senior project and has been working with people on how to integrate systems. So now I was able to help us, and then just being here for hours trying to figure out how this all works and just keeping our heads down and going at it. it really taught me how to have a little bit of grit in a project like this. And pass it on to Seb.
I totally agree with you about what you said about challenges, because I think for me the biggest outcome of this project was debugging and troubleshooting. Because in our labs we have, our lab instructors Nate and Jaime. They're super great, super helpful. Every time I have a problem, I raise my hand, and Nate's right there and he fixes the problem. But here we're on our own. One of the main examples would be the Hall effect sensor. When I hooked it up directly to the Nano, it would only read between 0 and like 1.7, so it wasn't high enough to actually actuate anything. And that's due to the fact that the Nano doesn't have any internal pull-ups or pull-downs. So I had to do some research and devised an external pull-up for the sensor, which now works properly. In addition to the troubleshooting Linux, I had never used Linux before, and so it was a lot of research in how to configure that properly. But yeah.
But yeah, all in all, I think we're really happy for our initial prototype. We had all functionality working great, and so now the obvious step would be packaging and getting the spaghetti wires in a nice manner. We have some ideas for that. Potentially we could continue on this project later, but all in all, I had a great time doing it.
Agree.
Thank you.